Hey, Algebra 2, welcome back to day 2 of lesson 53. We're going to continue to practice some composition of functions, and then we'll finish with where we can apply a composition of functions to a shopping example, which we have on example 5. But looking at example 3, we're going to start to look at how the composition of functions are not commutative, and how if you change the order of how you are finding your composition of functions, it will give you different results. So first we're going to look at what is the composition f of g of x, and then what is g of f of x. I'm going to use the space over here, and first we'll have f of g of x, and I'm going to use this type of notation. And then secondly, we'll go with g of f of x. So I start with the inside, which is g of x, and I'm going to take g of x. What that's communicating to me is to take x and put it into your function. Well, all that happens when I put x into my function is I would just be left with this function rule, 3x. So the g of x function, when you input an x, your result or your output is just 3x. And then following what we did yesterday, you're now going to take the output of your g of x function, and that's going to now become the input of your f of x function. So we're going to now take the f of x function, and we're going to input 3x into it. And going to look at my function, it's 4x minus 6, so that means I'm going to take 4 times 3x and then subtract 6. So all I'm doing is taking the input of 3x, taking the x out, and replacing it with that 3x. And I end up getting then 4 times 3x is 12x minus 6. So when we do our composition of functions, f of g of x, I get the result 12x minus 6. Now we'll flip that around. We'll look at what happens when I do g of f of x. So g of f of x, the f of x is on the inside, so that is done first. So f of x is equal to 4x minus 6. So when I input an x into this function, that's my output, 4x minus 6. So then that now gets input into the g of x function. So just like yesterday, we take whatever the output is, and then we're inputting that into our next function. So 4x minus 6 now inputs into the g of x function, and the g of x function is 3x, and this is communicating to me take 4x minus 6 and put it in for the x. And I apologize, my writing isn't the best there, but we'll take 4x minus 6 and put it into the g of x function. And we do any cleaning up, this would cause us to use the distributive property, and we'd end up with 12x minus 18. So there we can see that in each case, when we flip the order, the results are going to give us different answers. So we can get the proof of that when we flip the order, the f of g of x or g of f of x, we start to see different results. And we'll also see that when we input numbers. So here we have f of g of x and g of f of x, and this time we're going to do x equals 2. So let's start with f of g of x. So we take f of g. We want to input a 2, so I'm going to take x out, put a 2 in, and figure out what the answer is. So this would tell me first to take g of 2, which g of 2 means put a 2 in for the g function, which 3 times 2 is equal to 6. So we get g of 2 is 6. Then that output now becomes my new input into my f function. So remember, you're always doing your function on the inside first. So f of 6 now is going to be 4 times 6 minus 6. And that's going to end up being 18. So there's our final result after running the function through twice. Secondly, we'll take our g of f of 2 and just show that it does give us a different result. So g of f of 2. So this is communicating to us first do f of 2. So f of 2 would mean that I would take the 2 and put it into the f function, which is 4 times 2 minus 6, which is going to just coincidentally be 2 again. So 4 times 2 minus 6 is going to equal 2 because 4 times 2 is 8. And then that 2 then now becomes the input into my g function. So remember, you always start with the inside first. F of 2, figure out what that is first. It ends up being 2. That's just a coincidence. Now I'll take my g function, 3 times 2, and we'll get our final result of 6. So again, we can see that this answer gave us 18. This gave us 6. We do see a different result for each of those. So that is just kind of proving that when you flip the order of how you run your answers through your function rules, that you will get different results. In example 4, we're going to do a composite function with 3 functions. So this is something that we're just going to introduce. It's not something that Delta Math will practice today. But here we'll take f of g of x, we got 3 of them, f of g of h, and I'm going to actually color coordinate this a little bit better. So we'll go f of g of h of x. So there we can kind of see each function. So the h function is inside the g function, and then the g function is inside of the f function, which is the red. But we're still sticking to our exact same process. We are first going to start with that inside function. So we start with h of x, and h of x, all we know about h of x is it's equal to x squared. So that would represent the output of the h of x function. And then that now becomes the input into my g function. So we're just going in order. So we're just going to take each output of the previous function, input it into the next function. So now g of x squared, I take the g function, which is 2 times x squared plus 3. So that result I got for the h function, when I put an x in for the h function, it still just gives me x squared. That output now becomes the input into my next function. And we'll just kind of clean this up. All we can do is make this 2x squared plus 3. Now that output becomes the input into my f function. So lastly, I'll take f of 2x squared plus 3. And the f function is just negative x, so this becomes negative 2x squared plus 3. Which that negative in this case algebraically just kind of represents a negative 1. We can distribute out to both, so then we end up with negative 2x squared minus 3. So that would be running all 3 functions. We get a result of negative 2x squared minus 3. So you could keep going beyond this. We could go throw it back into the h function again. We can just keep running functions continuously. So there we can kind of see how we can run a example where we're going through 3 different functions. Lastly, let's take a look then at an example that we can find our composite of functions using a real-life example. So a local travel agency is offering a special on selected trips into several cities in the United States. If you book within the next 30 days, you receive a 25% off the original price. So there's going to be one of our situations, so 27 or 25% off the total price. Secondly, we get a 10% discount if we pay in cash. Find a function that describes how much a customer pays for the trip if the customer pays in cash for the trip at the same time that it is booked. So we're going to find what's the total if we pay in cash and we book it within these next 30 days. So there's my 2 situations. So we're going to have 2 functions. First function, we'll just, let's see. So we can call it, we'll call it f. We'll just call it, stick with our same Same idea. So f of x is going to represent my 25% discount. So if you're getting a 25% discount, that means you're still paying 75% of the original price. So I would have 75% times x. X represents the cost of my trip. So maybe I'm booking a trip for $10,000. Now it's only costing me $7,500. Next, I have a g of x. So we'll use g of x to represent if you pay in cash. So if you pay in cash for your trip, you get an additional 10% discount, which 10% discount, I should clarify there, that's going to actually mean I have to pay 90% or 0.90 of that original cost. Now, if I pay cash at the same time it's booked, now that's going to start to represent my composite function. So first, I can write my composite function. This is going to be f of g of x. And there's going to be my two functions working together. So first, g of x is equal to 0.90 times x. That now inputs into my f of x function. So I'm going to apply both of these functions back to back on my trip cost. So now I'm going to find what is the cost of my trip if I run it through both discounts. So I get the cash discount and I get the booking in 30 days discount. So f of 0.90x, that's going to leave me with then my f function was 0.75x. So 0.75 times 0.090x, and we end up getting 0.75 times 0.9, which is going to give me 0.675x. So when I apply both discounts, I'm really going to save about 32.5% total if I can get both of those discounts put together. Now the common mistake would be to do 25 plus 10% and think you get 35% off. But once you apply a discount, you have a new price, and then now you're finding a percent of that new price. And that's why it ends up only being a 32.5% discount. Well, that finishes up Lesson 53, Day 2. Thanks for joining, and we'll see you next time.